Hello 171 class, this is your notes for section 2.5, the zeros of polynomial functions. So this is probably, in my opinion anyway, the toughest section that we do in this course as far as material goes. It's imperative that you practice it early and often if you want to do well on this quiz and this material. Alright, now we do use this material in other sections. It doesn't get nearly as in-depth as it does in this section, but we will use it in 2.6 and some of the sections going forward. But just know that it does get tough, and you are going to have to really put in some work and effort to get this section. Alright, so first thing we talk about in here is something called the rational zero theorem. And what the rational zero theorem tells you is if, okay, big word here, big important word here, if there are, if we have integer coefficients, right, all these a sub n's and all these a's are integers, whole numbers, plus or minus whole numbers, basically. And there is a rational zero, meaning that some fraction, when I plug it in for x, it makes this polynomial equal 0. If that's true, if there is a rational zero, then it has to be the numerator of that rational zero divides this constant term, and q, the denominator of that rational zero, divides the leading coefficient. Okay, now it is important that p, the numerator, comes from the constant term, but what's the most important, vitally important that you understand this, is that q, the denominator of these possible zeros, divides the leading coefficient. Those two are linked. So denominator and leading coefficient. It's going to be very important that you understand that part of it shortly. So in summary, what the rational zero theorem says is possible rational zeros, again, rational means like a fraction, is always equal to plus or minus, meaning this could be positive fraction or it could be a negative fraction. And then the numerators will be factors of the constant term, right? That's the last thing. And the denominators will be factors of the leading coefficient. So that'll always be the case for rational zeros. Alright, so we're going to look at some examples of how to use this to come up with some possibilities. Okay, now remember, these are possible rational zeros. These aren't the rational zeros. So it's really important that you understand that too. We're finding potential candidates that make it equal to 0, not the things that do definitely make it equal to 0. Alright, list all the possible rational zeros of this. So the leading coefficient here is equal to -1, right, the number in front of x to the 4th. The constant is equal to 4. Okay, so it's going to be possible zeros are plus and minus the factors of the constant divided by plus and minus the factors of the leading coefficient. So the factors of the constant, what I do here is I just list them. The factors of the constant, the 4 are 1, 2, and 4. And the factors of the leading coefficient is a 1. Now it could be a 1 and a -1, you know, but it also could be a -1 and a -4 divided as 4. So we don't have to list the signs because we got the plus and minus here. But then we make every pairing that we can here. So plus and minus 1 divided by 1. 1 divided by 1 is 1. And then plus and minus 2 divided by 1 is 2. And then plus and minus 4 divided by 1 is 4. So these are the possible things that can make this equal to 0. None of them have to. It's just if there is a rational, and these are rational because we can write them as a fraction. 2 over 1 is the same as 2. If there is a fraction, a rational number that that makes this thing equal to 0, then it's got to be one of these 6 numbers. 6 here, there's 3 absolute values, but then positive or negative each one, so that's 6 total possible things to try to make that equal 0. Alright, same thing here. Leading coefficient is positive 1, and then the constant term equals negative 6. So our possible rational zeros are plus and minus all the things that divide the constant. So that's 1, 2, 3, and 6. Okay, again, we don't worry about the sign because it's taking place right here. And then the leading coefficient is 1. So 1 divided by 1, 2 divided by 1, 3 divided by 1, and then 6 divided by 1. So what you're hopefully seeing is if your leading coefficient is 1 or negative 1, then your possible rational zeros are going to be whole numbers or integers, positive or negative whole numbers, which makes the work nice. But your leading coefficient is not always 1. Alright, so here's an example where the leading coefficient is not 1. So our leading coefficient is 6. Our constant term is 3. So the possible rational zeros are plus and minus the factors of the constant term, which are 1 and 3, divided by the factors of the leading coefficient, which are 1, 2, 3, and 6. And again, we make every single possible fraction we can make here. So I'm going to start with the 1. Use every denominator. So that's plus and minus. 1 over 1 is 1. 1 over 2 is 1/2. 1 over 3 is 1/3. And then 1 over 6 is 1/6. Okay, and then the same thing with the 3. So plus and minus 3 over 1 is 3. Plus and minus 3 over 2 is 3/2. Plus and minus 3 over 3 is 1. I've already got 1, so I can skip that one. And then plus or minus 3 over 6 is 1/2, which I've already written, so I can skip that one. Alright, so there's all the possibilities. I rearrange them by smallest to largest. You don't have to do that. And then you really have to, you're supposed to put this plus and minus in front of each one. So plus and minus 1/6 is the smallest. Plus and minus 1/3 is the next biggest. Plus and minus 1/2 is the next. Right, and then plus and minus 1. Plus and minus 3/2. And then finally, plus and minus 3. Alright, so that's smallest to biggest. And it's positive, it's the positive and negative, the opposite of each one of these are your possible zeros. Now, none of them have to work. If I plug in each of these numbers, none of them have to make this 0. It's just the things that are possible. Okay, so that's the big thing that you understand here. Okay, constant factors on the top, leading coefficient factors on the bottom. Make every fraction you can with them. And then, like we did before, 3 over 3, 3 over 6. These are redundant. I mean, we already had them. 3 over 3 is 1. 3 over 6 is 1/2. We've already got them listed, so we don't have to list them again. Alright, now if you're told to find all the zeros of one of these functions, if you're using the rational zero theorem, our rational zeros here, the factors of the constant, are 1, 2, 3, and 6, and the factors of the leading coefficient are 1. So it's just going to be plus and minus these whole numbers. Alright, so there's our possibilities. What I'm going to do now is I'm going to plug this thing into the calculator. Alright, now I've got it in there. The next thing I'm going to do is I'm going to press second window, which is above here. You see it says table set. Alright, so the thing that we want to do, if this isn't 0 on 1 for you, that's not a big deal for now, but typically we want to make those 0, 1. And then we want to come down here to independent variable, that's the x's, and we want to tell it to ask us the independent variable. Alright, then once we've done that, go to second graph or table. Alright, now you see it's completely blank. It's waiting for us to put numbers in. And this is the numbers that we're going to put in. We're going to put in plus or minus 1, 2, 3, and 6. So we'll start off by putting in 1, and then negative 1. Alright, and then we get a 0. Whenever you see a 0 underneath y, that's a 0 of this polynomial. Okay, and now 2, there's another 0, negative 2. Alright, 3, negative 3. Alright, there's a third 0. Now I'm going to show you the other two. 6 and negative 6 don't work. But once your degree, this is degree 3, once you have that many zeros, remember we talked about that back in section 3 when we first introduced polynomials, that the degree of the polynomial tells you the maximum number of x-intercepts. And the x-intercept is a 0, a real 0. So we've got 3 real zeros, we can't have any more because the power is 3. So once I found that third one, that negative 3, I really didn't need to do the 6's, but I just wanted you to see that the 6's didn't work either. So those are all the zeros, negative 1, 2, and negative 3. Now typically you write these inside a set bracket, and you would write them in an increasing order, so negative 3, negative 1, and 2. But you don't have to write in that order. As long as you get the 3 zeros in there, it's fine. Okay, but that's how we use our calculator to do this. We use the tables setup. Now, if I kept this at auto, I could still find these zeros. It's just going to give me other things too. Okay, it's going to give me like the 5. We didn't put 5 in there. And I just have to scroll a little bit more. So there's the 2, there's the negative 3, there's the negative 1. Okay, I can still see them. I'm just looking for where there's a 0 in that column. It's just that I'm going to get some other things that aren't the zeros. Okay, now the benefit of this, the benefit of being in auto mode instead of ask, is that you don't have to do the rational zero theorem. You don't have to pick the numbers or find what numbers that you're going to plug in there. You just kind of scroll until you see zeros in this right column. Alright, so that's kind of a way to bypass the rational zero theorem a little bit. The rational zero theorem will shrink down the number of things that you got to check, but you know, taking the time to find them all. And sometimes, I mean, there's only 8 here, but sometimes there could be, you know, 36 of them. You know, it just depends on what the leading coefficient and the constant term are. But anyway, you can use that table in auto mode and seek out zeros. Alright, so there's what we did. There's some instructions. I'll post this to Moodle, so you'll have something that you can print out and look at. You can also pause it right here and kind of get it down. But I'll put this on the Moodle, so you'll have the ability to print this and look at it. Alright, but that's what you're looking for, is zeros in that right column. Alright, let's practice another one here. I'm going to plug this into the y equals. Alright, so there's the function plugged in. I'm going to go to second table set. Okay, I'm just going to leave it. I usually make this start at 0, but I'm going to leave it auto this time, and then second graph or table. Then I'm looking for zeros in this column. So there's a 0, so I know 1 is a 0. Oh, that's right, you can't scroll up unless you're in the X column. You can scroll down in y but not up. Okay, and then there's -5 and -4 also. Alright, so I got those three zeros. -5, -4, and 1. Now, don't be fooled by this one. You're not looking for zeros in the x. Okay, this is a polynomial. Domain of a polynomial is all real numbers, so there's always going to be a 0 underneath x, in the position where it's supposed to be. It's the zeros underneath the y's that we're looking for, and the x's that make those things the y's equal 0. So -5, -4, and 1. Alright, now the thing that you got to understand here is that not every single time are you going to end up with integer zeros. Okay, remember, you're looking for the same amount of zeros as this degree, but if you recall from section 3, the degree of the polynomial tells the maximum number of x-intercepts or real zeros. It doesn't have to be this number. Okay, our calculator may not be able to find everything, but even if there are whatever the degree, like this degree 3, even if there are 3 real zeros, they don't all have to be whole numbers. Okay, we've got a vast majority of these possibilities here are fractions. We got 1, 2, 3, 4, 5, 6 times 2 because of plus or minus. That's 12 whole numbers. We got 32 here total. So we got 20 fractions, 12 whole numbers. So we got a much bigger number of possible fractions than we do whole numbers. And again, if you look at this table, the x's that it picks are always whole numbers, right? Initially, that's all dependent upon the delta table, right? The little triangle is red delta. So when the delta table is 1, that means it's going to add 1 to whatever you tell it to start with. So you tell it to start with 0, it's going to move up and down by 1 unit each time. So what we have to do, this is where you have to understand the rational zero theorem. The denominator for the possible rational zeros comes from the factors of the leading coefficient. What are the factors of 18? Well, it's 1, right, for the whole numbers, 2 for all these halves, 3, right, then 6, 9, and 18. Those are the possible denominators here. So when we use, I'll say technology, but basically the calculator, when we use the calculator, what we're going to do, instead of plugging in every single possible one of these fractions into the table, which would take forever, what we end up doing is look for whole number zeros first, because that's what the table is by default. The delta table is 1 by default. So we're going to look for those first, scroll up and down and see if any of these zeros work. And then if we don't find 3 zeros, the next thing we're going to do is go to the next biggest denominator. Right now our denominator is 1 because we're looking at whole numbers. Then we're going to change the denominator to 2, and we're going to look for these halves. And then after that we're going to change the denominator to 3 to look for the thirds. And then we'll change the denominator to not 4 but 6. Okay, it always goes by what's the next biggest denominator. Alright, and it all comes from the leading coefficient. Another reason why the leading coefficient is so important. Alright, so let's look at this particular polynomial. So I plug in the polynomial. I initially make the table start at 0 and delta table equal to 1. I hit second graph, right, to give me the table, and this is what I see. 0 to 6, I see numbers getting bigger. I scroll up, I don't see any zeros. I scroll down, I don't see any zeros. I could go up and down all day long and never see a 0 in the y column because there aren't any integer zeros. There aren't any whole numbers, plus or minus whole numbers, that give me 0. So what do I do? Here's my list. Notice the next biggest denominator after the whole numbers, after a denominator of 1 is 2. So because the next largest possible denominator is 2, now I change delta table to 1 over 2, which is the same thing as a half. Now, I literally put in 1 over 2. Like when I go to table set, I change this to 0, and then I change this to 1 divided by 2. 1 divided by the next biggest denominator, but when I hit enter, it by default goes back to a decimal. Alright, and then when I scroll up and down, now I see a 0 when x is 1 1/2. Okay, 1 1/2 is the same thing as 3 halves. Okay, or 1.5. So 3 halves is a 0. Okay, but then I scroll up and down, I don't see any more zeros with the halves. So after I get my first 0 1/2 and I'm done with the 2's, I still have the possibility of 2 more zeros. So the next biggest denominator is 3 after 2. So then I change the delta table to 1 over 3. And again, when I change it to 1 over 3, initially I write it this way, 1 over 3. Okay, and then I hit enter and it changes to a decimal. Okay, and then there's the 0.33333 and then negative 0.13333 repeating. So those two numbers, and those are the values. Now, you might ask, how do I know that those decimals are these fractions? Well, I just know, okay, but your calculator can find them also. So from your home screen, second quit to get back to the home screen from the table, if you type in so this is 3 repeating, if I type that in a whole line of a bunch of 3's repeating, and then press math into a fraction, my calculator says that's a third. Okay, and then if I did negative 1.3 and it just filled up a whole line, then math into fraction, the calculator says that's negative 4/3. So your calculator can change these things to fractions as well. Okay, typically it's going to be looking for fractions. It'll ask you for fractions for these answers. Alright, so there's the zeros. I've got a degree 3, so I'm done. I've got 3 zeros, it's degree 3, I don't have to look anymore. Okay, but if, for instance, if I got to 3 and there still were zeros left, I wouldn't go to 4 or 5. Okay, 4 is not a possible denominator, nor is 5, because they don't divide that leading coefficient. They don't divide 18. 4 doesn't divide 18. 5 doesn't divide 18. So I wouldn't make the delta table a fourth. And I wouldn't make delta table 1/5. The next thing I would do is 1/6, because 6 divides 18, and then 1/9, because 1/9 divides 18, and then finally, if I needed to, if I still hadn't found 3, 1/18. Okay, so 1 over all these numbers, 1 over 1 is 1. 1 over 2 is a half, 1 over 3, 1 over 6, 1 over 9, 1 over 18. That's the things that you're going to change delta table to.